Alright guys, so this is for you guys, y'all out there. So basically, I was looking in Space Engineering. I found this one particular angle, uh, where you can see the orbital trajectories of all the planets and, stars, around this one supermassive black hole that holds an irregular galaxy together, or AKA IRR galaxy. Um, So the IRR galaxy was very interesting, actually. I'll show you in a minute, but I'll just it's right over here. Yep. Okay, so I'll just show you the irregular galaxy right now. Let's just select that again. Okay. So so I can zoom out right now and show you really quickly. All right. And this is the irregular galaxy. It's a very interesting galaxy because it's not in the shape of a spiral. It's not even elliptical. It's irregular, and I couldn't agree more. But that's the galaxy. So I'm gonna go back to the snipping tool that I have. Obviously, because I don't have any other tool, I'm just gonna use the default Windows one. Unfortunately, I cannot really write on this, which is why I have to type. So but wait, no, I have to write it. I just can't type on it, right? So I'll just I'll just talk as I do it. All right. So let's say we have this area right here. So let's focus on this one place, right? These curves. All right. So I'm just going to go over them a little bit. Yes. Okay. So theoretically, these curves, every segment of them, which I'll be separating right now, every segment we conclude with these crossheads. But let's say that I took obviously this isn't the center of the black hole where we're looking at. We're looking at a little slightly right of center. But say we did take a photo of the center, then all these orbits would theoretically, because of the way they're aligned, look like a constant width curve. Constant width curves kind of look like an egg, as you can see right here, right? So if you have a constant width curve, all right, you can calculate a constant width curve by just making a triangle, any triangle really, right? So we have a triangle right here, one here and one here. All right, we got points. Let's label this A. All right, this is going to be B, and this is going to be C. All right. So this is our triangle. Actually, I should move C because it's going to be overlapping my my line here. Wait, no, that's a bad place to put it too. Let's put C over here. All right, there we go. So basically, we can connect these lines to finish the triangle. It's just going to be easier for us, right? Connect these points. And what we can do is we can extend them. Alright? We'll extend it just a little bit from every side. Alright? Very easy. Now what we do is we're going to make a curve here. We're going to make an arc. Basically what we do is we take C as a focal point. We create a circle. We cut off most of the circle and only savor this one arc. And then over here, then B is going to be the center, because we're going to extend this line over here. So now B is going to be center. So we just switched our focal point from point C to B. And remember, this is just a intro lesson for those of you who don't know what constant width curves are. Then we extend the line from A and we make another curve right here. And you can see it's starting to make its egg shape, I guess. Then you take C as a focal point, and I already extended B, so that's good. I should probably edit that line because it looks a little too long. Alright, here. Alright, and we'll just do it again. Alright. So remember, these aren't accurate drawings that I'm making here. Alright, this is just, I'm very bad at drawing with a mouse. I know I should be using a different tool for this, but you know, whatever. Crap. See, this is, I guess these are the points in time where you actually need a touch screen. The very few times in your life where you actually need a touch screen. Okay. And we finished that with making point A our focal point. So this is going to be our constant width curve. Alright, and it's going to be the same thing here, basically. Alright? But here we have it separated in some very unique places. Alright? Our constant width curve is closed. This constant width curve closes and then flattens out right over here-ish, and eventually leaves. It escapes. Because of the gravitational lensing, we can expect that. It's nothing serious. It's perfectly normal. So what we can do is we can close the constant width curve as it would be if it actually was a constant width curve and these lines wouldn't extend outwards. Now I know that's literally impossible, literally and physically impossible, because as closely as this resembles a constant width curve, it's never going to be a constant width curve. So our measurements here are never going to be accurate because we are making assumptions here. Remember, we have literally no data. We have pretty much no data. We don't know the angles. We don't know the distance of the gravitational lens, because even if we did calculate the distance with the space engine, it would give us some incredibly either small or large number. I can't comprehend it right now because of the gravitational lensing. I mean, this lens, though it may look like it's very close to this, might be light years away. Because of the gravitational lens, you have to go in the path of the curved space-time, and it's just gonna take a while. It's not gonna take light years, but you know what I mean. So everything here is approximated. We're just assuming that there's going to be some sort of triangle inside this black hole that's creating a constant width curve. I'll leave this drawing up here just for reference, so you guys won't be confused. Also, if you're hearing music in the background, that's perfectly normal. I'm actually listening to the Bees Gees right now. I don't know why, but so yeah, we can determine that this is going to be a constant width curve, or we can assume. So basically, what point am I trying to get through here? Well, I want to do a little bit of calculus. All right, and I'd like to see what the area of this place is. Let me just alright, I'd like to see what these areas are. I've never done calculus before, but I'm assuming that if this is a perfect constant width curve, all these areas are going to be the same area. I mean, I have done calculus before, but it's not. I haven't done it like this way. It's I've done it on much simpler scenarios. Yeah. So basically, my goal here, everybody, is to just find the red areas of this area, of this place, right? Of the gravitational lens. So what will this prove? What will all this prove? Well, this will prove that black holes can have the potential to create a gravitational lens that will create a constant width curve, or create something near or close to a constant width curve. Why is this fact interesting? Well, a, a constant with curve is interesting to begin with. Alright, a constant with curve is... Alright, let me start it out this way. How would you define a circle? Right? Just this simple, small, little figure right here, which is a fail of a circle. But, how do you define it? Would you define it that as long as you go through the center... Yeah, let's just say this is the center. Remember, I suck at drawing. But will you define it that if it goes through the center at all times, and the length between points A and B, or B, C, A, B, and then, C, D, E, F, do you think that they will be the same? Is that your definition of a circle? Or is your definition of a circle something different? Well, most people would actually say that answer that I just, told you. That as long as you go through the center, which we're going to call A, and the distance, right, between here and here, and the distance between here and here, basically these two line segments would be equal to x, right? That's wrong, because that's exactly what happens in a constant width curve. Now I'm going to redraw my constant width curve because I don't feel like destroying this. So we draw a triangle here, all right? Really quickly. We're not gonna have time to label anything, so we're just gonna make it really brief, I suppose. So yeah, we're gonna make a constant width curve right now. Hold on. So the distance between here and here, basically this line segment right over here, is going to be x. The distance between here and here is also going to be x, and the distance between here and here is also going to be x. Every line segment that goes through this triangle in this definition would have the same length, or width in this case, because it's called constant width curve. And it's very interesting, because, what other image in the entire universe has this property other than constant width curves and circles, right? So it's an interesting fact. So now that I know about that, I'm just saying that a circle, one of the unique properties of a circle that no other figure has, is that the circle, let me just draw it again, and you have a center right here. So the circle, if you have a radii that points out this way, and you have another radii that points out this way, and let's just extend these for the sake of simplification. So the point of a circle is that it's going to be tangential, right? The point of the exact point that the radii hits from point A to the crust, or to the outside of the circle, is going to remain tangential. Tangential means there's going to be a degree of 90. Now remember, this isn't, I'm not saying that at here it's 90, I'm just saying at here, at the crust. I just don't want to draw it there because it's going to be too confusing. So same thing here, it's going to be like a 90 degrees. Alright, so you can keep on continuing onwards and onwards, and it can be either direction, doesn't matter, as long as it's 90 degrees, you got it. So that's going to be your that's your thing, right? That's how you define a circle. Okay, so yeah, this is a very interesting scenario, because constant with curves are very interesting, and to find that a black hole can create such a thing is phenomenal. And what's even more interesting is that the centerpiece is just marvelous. This centerpiece is pretty much the thing that intrigued me, I guess, more than the outside that created a constant with curve. Because this is incredible, right? You're making it's not even a defined figure. It's you can't describe gravitational lensing. It's just so irregular, but it's so fun at the same time. Cause look at this, right? Can I zoom in this? No, I can't. All right, I can't zoom in this, but I can at least point out some things to you. This image looks like another constant with curve, right? But this is not caused by lines being bent. You know, it's not caused by something that looks like this. Rather, it's being caused by... Let me just draw... Okay, this kind of looks like an oval, I guess. So, I mean, this is a black hole, right? Let's just color code that in. And this is what happens. You get a line right here, goes along the surface, comes back right here. That is incredible. What other figure out there does that? Now let's imitate these two lines, assuming that they're perfectly symmetrical. Right? I mean, we don't want to screw anything up here. So we're gonna do this. There's just for the sake of it, because I saw another one right here that was just like this. And what's interesting about this one is that it goes right over here, and it kind of overlaps. Yeah, it does overlap right here. So I did that actually. I guess I didn't make a mistake there. And there's another one that overlaps this, comes around here, and overlaps this one and makes this. So you made a constant with curve by combining 3 different circles. And let's just ignore the centerpiece, all right? Because this is confusing enough. We don't want a centerpiece. I mean, I'm only a kid. I'm 14 years old, right? I mean, anyway. So I mean, it's awesome. It's very interesting. So, I mean, we can use calculus. Alright, my friend's speaking German, I guess. I don't know. Anyway, so I'm just gonna color code these because I want to signify the areas that I want to calculate. So I want to calculate pretty much all the overlapping areas and all the gaps. And I want to add all those areas together to see if I can find some sort of, I guess, interesting number. I mean, who knows? Maybe it'll equal some other value. That would be pretty remarkable. That would be good discovery, actually. Maybe I shouldn't post this video. But you know what? I'm just gonna post it out there for you scientists out there, or any viewer out there. Just take advantage of this video. Feel free to solve it for yourself, I guess. But you know, I don't really care. It's okay with me. But I recommend solving this because it's so interesting. I mean, I know there's going to be a lot of viewers out there who's going to call me a nerd, right? For example. I know that because, I mean, I am a nerd, and I'm sitting here wasting my time talking about math in the middle of the summer. You know, it's a really interesting thing to do, even if it's summer. It's just fun. So take a moment, suck this into your brain. Just remember the definitions of constant with curve and circles. Go ahead and calculate the use calculus if you can to calculate the area, the gaps and such. So I'd like it if I could exchange my answers with you, so we can come up with something here. But let's say, I mean, we're going to have to come up with definitions here. All right, you know what? How about this? I'm going to. All right. So let's go to. Okay, I'm going to tell you the name of the black hole. All right, I'm going to tell you the name of the black hole in the description. It's going to be a long name, but it's going to be fine. Just type that in. Get Space Engine. Space Engine is a free game. It's only 920, I think, megabytes. I'm not sure. I'm going to have to check later on. But it's an incredibly small game for its graphical design, and I mean, it's free. You can go to en.spaceengine.com, I believe. If that doesn't work, just search up Space Engine. Make sure you don't search up Space Engineers. That's another game that has nothing to do with this. So they're completely independent of each other. Just do not search up Space Engine. Space Engine, not Space Engineers. Okay, so yeah, just go ahead and search that up. Go ahead and download it and plug in the name that I sent you. That I guess plug in the name in the description of this YouTube video, and just put it in the search icon, I guess, and it'll hopefully automatically move you there. It's not a randomly generated thing here. It's actually a legitimate object that we named. That computer's named, actually. So yeah, it's just go ahead and do that, and we're going to, just for reference, so don't use that for any calculations. We're gonna come up with a standard here. All right, so let's say the center of this black hole, all right, the radius from the center of this black hole to out here, ignoring space-time, let's say that it's going to be 1 astronomical unit. All right, 1 AU, 1 astronomical unit. Again, I have no idea how the heck I'm going to be able to calculate the distances. Remember, I'm not in calculus yet, but I'm going to try to do it. So let's say that's 1 astronomical unit, and from here, I guess the radii from here to here is going to be 0.7-ish, 0.75, let's say 0.75 AU. Yeah, that sounds good. So yeah, this is going to be 0.75 AU, and that's going to be 1 AU. So yeah, go ahead and get those numbers into your brain. That's going to be awesome. If you want, you can go ahead and take a screenshot of this video at this time. That's going to be pretty much all I need to say right now. Yeah, let's actually, I don't know if I need this or not, or if you guys need this or not, so I'm just gonna write it anyway. Let's make a little triangle here just for reference, and the center does not go into the triangle. It's just, remember that, center does not go into the triangle. Label this A, label this B, label this C, okay? And okay, this is going to be 0.1 AU. The distance from here to here is going to be 0.12, because that looks like 0.12, right? Doesn't it? And the distance from here to here, just right down there. Okay, so and the distance from here to here, I'd say it's going to be B and C look closer to each other than A and B, so let's say 0.09 astronomical units. Yeah, AU. Remember, all these calculations are based off of relative sighting. They're not actually correct, but we're speaking approximations here, right? And relative magnitude. So these are your dimensions, I guess. Remember, 0.12 for AC, 0.1 for AB. BC is going to be 0.09, and 0.75 astronomical units for the smaller constant width curve, and 1 AU, 1 astronomical unit for the bigger constant width curve. That's all I need to say for you guys right now. Go ahead and calculate. Use calculus to do that. If there's anything else you need, I'm going to just type down your questions in the comment section, and I will try to answer them for you by approximation, of course. Remember, we can't actually measure this because it's just a computer game. We can't, and it's not meant for this intense, or it's not meant for things for calculations this intense. So anyway, thank you guys for watching. It's been a pleasure, really, and I'll see you guys next time in the next video, and I hope you enjoyed. Goodbye.